Welcome back, everyone. Today we'll look at our third conic section, the ellipse. At the start of your lesson, you had the pre-video activity focusing on distances. If you haven't had a chance to work on it yet, pause the video to do that now. Before we go check your work, let's learn a bit more about the curve shown in this activity. We commonly refer to this shape as an oval, but as you might have expected, the mathematical name for this curve is actually ellipse. Recall that the ellipse is the third type of conic section, which results from intersecting a cone with a plane at an angle not parallel to its base. There's a pretty interesting way in which we can draw this ellipse precisely. Let's see what it is. First, picture placing two pins, one at point F and another one at point G. Then, imagine pinning one end of a string at point F and the other end at point G. Now, let's grab a pencil and use the tip of it to pull the string taut, placing the tip at the point 0, 4. Keeping the string taut, let's slide our pencil around the points F and G. And voila! We have an ellipse. As we further explore ellipses, keep in mind this drawing technique, as it will reveal some important properties of ellipses. Now let's look over the questions in the pre-video activity. To find PF, we can draw a segment connecting P and F and then find its length using the distance formula. However, in this case, I find it easier to visualize PF as the hypotenuse of a right triangle with legs 3 and 4 units long. Remember that the distance formula is just an application of the Pythagorean theorem, so if it's simpler to use the theorem directly, we can choose to do so instead of plugging the points in the formula. Using the Pythagorean theorem, we get that PF equals 5. Similarly, PG is also the hypotenuse of a right triangle with legs 3 and 4 units long. Therefore, PG equals 5 as well. What about VF and VG? Just by looking at our diagram, we can see segment VF is 2 units long, and segment VG is 8 units long. Take a moment to analyze these results. What do you notice? What do you wonder? I notice both pairs of distances measured segments with one endpoint on the curve and another endpoint at F or G. I also notice that both pairs seem to add up to 10. Do you think this is just a coincidence? Let's take a closer look at the official definition of an ellipse and see whether it sheds some light on this matter. An ellipse is defined as the set of points in a plane such that the sum of the distances from two fixed points, called foci, is constant. In this ellipse, points F and G would each be called a focus, and the plural of focus is foci. By definition, the sum of the distances from these foci to any point on the ellipse is constant, which means it does not change. This is why both the sum of PF and PG and the sum of VF and VG were both equal to 10. It wasn't a coincidence. It was the very definition of an ellipse in action for points P and V. Now, think back to how we drew this ellipse with the pins and the string. In your guided notes, write an explanation for why you think this method ensured the curve drawn was an ellipse. Pause the video now. Let's picture when the pencil tip was at this other point, P. How do we know for sure PF plus PG also equals 10 here? Isn't PF plus PG just the length of the string? As we drew the ellipse pulling the string taut, did its length change? No. If the length of the string was 10 for the points at the top and at the far left, it will also be 10 for any other point. Let's use this fact to find an equation for this ellipse. Let P be any point x, y on the ellipse with foci -3, 0, and 3, 0. Using these coordinates and the distance formula, find expressions for the distances PF and PG. Pause the video now and record them out yourself in your guided notes. PF simplifies to square root of x plus 3 squared plus y squared. Similarly, PG equals square root of x minus 3 squared plus y squared. Since these two distances always add up to 10 for this ellipse, making the sum of these expressions equal to 10 results in an equation that defines our ellipse. However, we usually write the equations of ellipses in a more compact form, which we call standard form. Let's simplify this equation until we get to the standard form, a process we call deriving the equation of the ellipse. Even though the main goal of this lesson is for you to work directly with the standard form, we will derive it together so you can understand where it comes from. The process can get a bit long and tricky, but just let yourself go with the math flow. Let's begin by getting rid of these square roots. We can undo square roots by squaring them, but will squaring both sides of this equation cancel out both roots? Remember, we cannot distribute an exponent over addition, but instead we need to multiply the entire expression by itself, which will actually not get rid of either of the square roots. Instead, let's cancel out these roots one at a time. I'm going to cancel the second root first. Let's isolate it by subtracting this other term on both sides. Now, squaring both sides will fully cancel out the square root on the left. What should we do on the right side? Here we'll have to expand. We can do so by multiplying the entire expression by itself using the distributive property. However, a more efficient alternative could be using the perfect square identity. A minus b squared equals a squared minus 2ab plus b squared. Try expanding the square on your own using whichever approach you prefer. Pause the video now. Expanding and then simplifying, we get 100 minus 20 square root of x plus 3 squared plus y squared plus x plus 3 squared plus y squared. Now we can do some cleaning up and work toward isolating the remaining square root to get rid of it. On your own, simplify this equation completely by expanding the squares and combining like terms. Then isolate the root. Here are the perfect square identities to help you expand. Pause the video now. We can cancel out y squared on both sides, then expand the squares. And cancel out some more terms. Next, we subtract the 100 and the 6x on both sides, which leaves us with negative 12x minus 100 equals negative 20 square root of x plus 3 squared plus y squared. Now, if you divided both sides by negative 20 to fully isolate the square root, you probably noticed we end up with a fraction. However, we don't really need to get rid of that 20 since it won't interfere with canceling out the root, because if we square this term as is, we actually can just distribute the square. That said, we can at least make the numbers a bit nicer by dividing by a common factor. What number would you suggest we divide by? Since there's a GCF of negative 4, that'd be the best choice. Now we're ready to square both sides again. On the right side, we simply square both the 5 and the square root, which results in 25 times x plus 3 squared plus y squared. Once again, expand the squares on your own and simplify any like terms you see. Furthermore, rearrange the equation so that all variable terms are on the left side and any constants are on the right side. Pause the video now and give it a shot. We expand the squares, distribute the 25, and cancel the 150x we have on both sides. Next, we make sure all variables are only on the left side by subtracting 625, 25x squared, and 25y squared on both sides, which yields negative 16x squared minus 25y squared equals negative 400. Lastly, we'll simplify these numbers by dividing both sides by negative 400 in order to get a positive one on the right side. On the left side, we divide each term by negative 400 and simplify all the fractions. Doing so leaves us with x squared over 25 plus y squared over 16 equals 1. We call this the standard form of the equation of this ellipse. Let's see what this equation can tell us about our ellipse. Take a moment to think about how the numbers in this equation might be related to the ellipse. Pause the video and write your thoughts in your guided notes. I notice the x-intercepts are negative 5, 0, and 5, 0, and I know 5 squared is 25, which I see in the equation. These 2 points also happen to be the ones that are farthest from the center of the ellipse, which in this case is the origin. We call these points the vertices, and that 25 in the equation actually determined that the distance between the center and each vertex is 5. We call that distance A, often referred to as the major radius. Furthermore, the segment connecting the vertices is called the major axis, which will always be twice the major radius, in this case, 10. What about the 16? Well, I notice the y-intercepts are 0, 4, and 0, negative 4, which might have something to do with the fact that 4 squared is 16. And indeed, it does. These 2 y-intercepts are the 2 points closest to the center, which we call co-vertices. The 16 in the equation is the reason why the distance from each co-vertex to the center is 4. We call this distance B, also known as the minor radius. Furthermore, just like we have a major axis connecting the vertices, the minor axis connects the co-vertices, and its length is 2b, or in this case, 8. Why does this equation work? Did you notice this equation looks a bit similar to that of another conic section? Picture taking away those denominators, leaving only x squared plus y squared equals 1. What shape do we get? That's just a circle, centered at the origin and with radius 1. How are those fractions turning this circle into an ellipse? To see what's happening, let's rewrite the ellipse equation so that it shows the major and minor radii. Because both numerator and denominator in each fraction are squared, we can also rewrite each term as a single square, and we get x over 5 squared plus y over 4 squared equals 1. But wait, these look like transformations of the circle. Are ellipses just transformed circles? Yes! Can you see what transformations are happening? Remember that operations done directly to a variable transform the graph in the direction of that variable, and in the exact opposite way we'd think they would. So even though we'd think dividing x by 5 horizontally should shrink the graph, it actually stretches it horizontally by a factor of 5. This stretch on its own would make the circle 5 times as wide. Similarly, dividing the y by 4 produces a vertical stretch by a factor of 4, which on its own would make the circle 4 times as tall. Doing both stretches together, we get the ellipse from our original equation. Now, let's generalize the equation of an ellipse. We saw how these denominators were the squares of the major radius 5 and minor radius 4. So in general, what will be the equation for an ellipse with major radius A and minor radius B? It'd be x squared over a squared plus y squared over b squared equals 1, which we call the standard form of the equation of an ellipse centered at the origin. In particular, this equation represents an ellipse with a horizontal major axis, which we can also call a horizontally oriented ellipse. Why is it important to specify this? Can we have an ellipse where the major axis isn't horizontal? Pause the video and try to draw a different ellipse, one that has a vertical major axis, and label its key features. An ellipse centered at the origin with a vertical major axis would look like this. We can also call this a vertically oriented ellipse. Notice how the vertices, center, and foci are now all vertically aligned along the now vertical major axis. Therefore, the major radius must now be measured vertically and the minor radius to the co-vertices measured horizontally. Does this impact the equation? Well, since the major radius is now vertical, we want to vertically stretch by a factor of a, and should therefore put the a squared under the y squared and the b squared under the x squared. This is why for a vertically oriented ellipse, the largest denominator will always be under y squared. Let's go back to the ellipse from the pre-video activity. Our original setup for the equation was PF plus PG equals 10, which was the length of the string which drew it. If we had known the values of A and B, we could have written the standard form directly from this definition without having to do the derivation process. Could we have used the foci and the length of the string to determine A and B? Let's see. Imagine pulling the string all the way to the left so that your pencil is at vertex V. The string is extended from G to V, and then it overlaps with itself from V to F. The string would span the entire major axis if it weren't for the little piece from G to the right vertex. But wait, isn't that length the same as the overlapping distance VF? It is. An ellipse is perfectly symmetrical across its axes. Therefore, if we fully extend the string horizontally, it will always measure exactly the same as the major axis. That is, 2a. And if 2a is 10, then a must be 5. How do we find b? Now imagine pulling the string to the top co-vertex. Notice the triangle formed by the strings and the x-axis. Can you figure out what the side lengths of this triangle must be? The base of the triangle should be 6, but what about PF and PG? Well, point P is at the exact place that makes PF and PG equal, and if the length of the entire string is 2a, or 10, then each side must be exactly a, or 5, which matches what we found in the pre-video activity. Can you see how we can get to B? Notice how the y-axis is perfectly splitting triangle PFG into two right triangles. The bases of each of those triangles would be 3, and the length of each base is the distance between the center and each focus. That distance actually has its own name, the focal length, C. Let's focus only on the left triangle. Can you see the relationship between A, B, and C? Since we have a right triangle, we can use the Pythagorean theorem. In this case, the hypotenuse is A, so the relationship becomes A squared equals B squared plus C squared. With this equation, we can find B by just replacing A with 5 and C with 3, and then solving for B. As expected, B equals 4. With this information, we can write the equation for this ellipse directly without needing to derive it. Here are the ellipse features and equations we have learned so far. If you haven't taken notes on all these yet, pause the video and do so now. Let's look at a couple example problems. Here's the graph of an ellipse. In your guided notes, complete the table with the features and the equation of this ellipse. Pause the video and try it out. We can see this ellipse is taller than it is wide, which means its major axis is vertical. It's centered at the origin because 0, 0 is equidistant to the vertices, and the vertices are at 0, -10, and 0, 10, which means our major radius is 10. The co-vertices are located at -8, 0, and 8, 0, which are each a distance of 8 units from the center, so B equals 8. To find the foci, we first need the value of C, which we can get using the equation a squared equals b squared plus c squared. Subtracting 64 on both sides, we get c squared equals 36, and therefore c is 6. This means each focus is 6 units away from the center along the major axis, so the foci are 0, -6, and 0, 6. Lastly, we write the equation using the standard form for a vertically oriented ellipse, substituting the values of a and b. Our equation ends up as x squared over 64 plus y squared over 100 equals 1. Let's wrap up our lesson with one last example. Graph the ellipse represented by the given equation and complete the table with its features. Pause the video and try it out on your own. Let's begin by identifying a and b. The larger denominator will give us a, and the smaller denominator will give us b. Since 49 is 7 squared and 36 is 6 squared, a equals 7 and b equals 6. The major axis must be horizontal because a is under the x. Here's our center, our vertices, and our co-vertices. We now have the necessary points to graph the ellipse, so let's connect them. Finally, we can use a and b to find that c equals the square root of 13, which lands our foci around 3.6 units away from the center at negative square root of 13, 0, and square root of 13, 0. It's important to note that the center and the foci are not actually part of the ellipse, but it's helpful to plot them for reference. Today, we learned that an ellipse is the set of points in a plane such that the sum of the distances from two fixed points, called foci, is constant, and that this sum equals the length of the major axis, or 2a. We also learned the standard form for the equation of a horizontally oriented ellipse, and for a vertically oriented ellipse. Lastly, we discovered that the parameters a, b, and c are all related by the equation a squared equals b squared plus c squared, where a is the major radius, b is the minor radius, and c is the focal length. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time! Hey, hey.